Okay, thanks everyone. Thanks for spending some time to come and find out about the superbugs. With it being Halloween last night, I thought it would be my job to come along and scare everybody. But unlike Halloween, this is a real threat, this is a real issue, and what I'm trying to do today is to get the message out to people that we need more and more people involved in this fight, this battle that we've got against the superbugs. My name's Pete Jackson. I'm the Executive Director of the AMR Centre based at Alderley Park in Cheshire. First of all, I'd like to explain to you exactly what antimicrobial resistance is. AMR. Basically, this is Darwin in action. The bugs are evolving to combat the threat as they see it from the antibiotics that we use that underpins everyday medicine in the UK and in the rest of the world. Whether you're having a caesarean section or a knee replacement or cancer chemotherapy, you'll be relying on antibiotics to keep you healthy through those processes. But someone once said to me this memorable phrase, they're clever little buggers. They can evolve many different resistance mechanisms to the drugs that we throw at them. So for example, they can evolve barriers so that the drugs can't get into the cell in order to kill the microbe. And then once they get in, they can evolve efflux pumps. So these are mechanisms to actually pump the antibiotics back out before they can have effect. They can develop enzymes. They can produce enzymes that will actually chew up the specific drugs and the drug types that we throw at them. And they can also develop alternative pathways around some of the enzymatic processes that are used to kill them. So, probably the most difficult is drugs are exquisitely designed to target particular segments of RNA or DNA to interfere with the microbial metabolism and to ultimately cure the patient and kill the bug. You can get DNA mutations that actually alter the target, so the drugs no longer interact. So you need a new drug in order to be able to hit this new target. So the really interesting thing is that many of these resistance mechanisms can be transferred from one type of organisms from another. So you've probably heard of Staphylococcus aureus, SA, as in MRSA. The MR is methicillin resistant, so MRSA is resistant to one type of drug. You now have multiply resistant strains of MRSA that are resistant to many of the different drugs that we can throw at them. And that's the same for other more dangerous organisms actually, such as Pseudomonas, E. coli, Klebsiella. So not only have you got single resistance mechanisms, you've got multiple resistance mechanisms in the same microbes. And very worryingly indeed, the last line of defense, a drug called colistin, we now have a gene called MCR1 which infers colistin resistance, and that's transferable again between different microbes. So we now face the prospect of having superbugs coming primarily from sources in the Far East, transferring in air travel, holidays, people travelling, global mobility. These are now starting to find their way into Europe and into the UK. There's a fantastic piece of work from Harvard that I'd just like to share with you now that demonstrates how this can happen. It's time-lapse photography on a gigantic scale Petri dish. And the thing to bear in mind is that what you'll see happens over 11 days. Now, most antibiotic courses that you and I take are for 7 to 14 days. So this timescale that you're seeing is on the same timescale as a treatment for an infection that you may be taking yourselves or one of your loved ones. Just let me show you this. Harvard Medical School, you can find the details online. It's quite a famous piece of film. So here we go.
So what we ended up building was basically a petri dish, except that it's 2 feet by 4 feet. And the way we set it up is that there are 9 bands, and at the base of each of these bands, we put a normal petri dish thick agar with different amounts of antibiotic. On the outside, there's no antibiotic. Just in from that, there's barely more than the E. coli can survive. Inside of that, there's 10 times as much, 100 times, and then finally the middle band has 1,000 times as much antibiotic. And then across the top of it, pour some thin agar that bacteria can move around in. The background is black because there's ink in it, and the bacteria appear as white. First, you see they spread in the area where there's no antibiotic, up until the point they can no longer survive. Then a mutant appears on the right. It's resistant to the antibiotic, it spreads, until it starts to compete with other mutants around it. When these mutants hit the next boundary, they too have to pause and develop new mutations to make it into 10 times as much antibiotic. And then you see the different mutants repeat this at 100. And after about 11 days, they finally make it into 1,000 times as much antibiotic as the wild type can survive. And so we can see by this process of accumulating successive mutations that bacteria, which are normally sensitive to an antibiotic, can evolve resistance to extremely high concentrations in a short period of time.
Scary, that, isn't it? First time I saw that, jaw-dropping. 11 days. So, said before about we all need antibiotics. Here's some statistics why this is absolutely critical. This is from the Department of Health and Social Care in the UK. So 1 in 3 patients in hospital at any one time will be on antibiotics. 1 in 3 of us will take at least one course of antibiotics during the course of the year. This is data here about bloodstream infections, so sepsis. 15% rise, 20% rise in sepsis caused by E. coli and Klebsiella. Infections are on the rise, resistance is on the rise. And 25,000 people die directly from a drug-resistant infection in Europe. It's the same number in the US. And there's about 700,000 people worldwide, with the heaviest burden falling on less developed countries such as India and China. But the real problem is that there are no new antibiotics. This timeline shows you when the antibiotic classes that we use today were invented. So back from 1928, Fleming, through to 1993 with the carbapenems that are widely used today. But it's been 30 years since a new class of antibiotics was developed. There are some new ones in the pipeline, but they're combinations, or they're second, third, fourth generation of the existing classes. They're a sticking plaster that will only buy us a few more years before the bugs evolve yet again to become resistant. Just let me show you how quickly this is happening. This is data from the Centre for Disease Control in Europe. 2002 surveillance data from each country in the EU. You probably can't read it very well, but dark green is less than 1% of infections. This is E. coli. Less than 1% of E. coli infections were resistant to fluoroquinolone. This is just to one type of drug. The yellow is 5 to 10%, the orange 10 to 25%, and the red is 25 to 50%. So in just 10 years in Southern Europe, half of all the infections, half of all E. coli infections were resistant to fluoroquinolones. And that was 2012, it's now 2018. Multi-drug resistant, and so now we're looking at Acinetobacter, another really dangerous pathogen. 2012, in some areas of Europe, there was no data because there was no resistant forms at that time. But look, this is combined resistance to fluoroquinolones, aminoglycosides, and carbapenems. So 3 whole classes of drug that don't work against these bugs. The purple is more than 50%. So if you go on holiday to Greece or Italy, then don't get an infection with Klebsiella, because it's a greater than 50% chance that it's going to be resistant to most of the drugs that are available. And definitely don't go and get a cut or have an operation in Egypt. This data for Klebsiella, samples taken from blood and samples taken from urine, between 53 and 95% of the samples taken, the Klebsiella samples found in patients, are resistant, and the list down the left are the drugs that are available to use in Egypt. So essentially, a major cause of infection is practically untreatable with the standard arsenal of antibiotics. It's this multi-drug resistant that's the real issue. So we have a growing problem, and we have declining solutions. So there was a major review on AMR, antimicrobial resistance, by Jim O'Neill, and they ran the model forward. There'll be 10 million people worldwide by 2050 that will die from a drug-resistant infection if we do nothing. Jim is an economist, so he was brought in to do this review to really bring it home to finance ministers around the world that it's not only a health impact, it's an economic impact. There'll be $100 trillion lost from the global economy due to AMR by 2050. That's 3.5% growth globally, lower than it would otherwise be. And 100 trillion, even by today's standards, is an awful lot of money. On the new drug side, you can see the slope here. You probably can't see. That's 2. There were 2 new antibiotics approved by the FDA between 2008 and 2012. And these were derivatives of the existing classes. So fewer drugs, rising problem. I told you it was a Halloween story. Just to make it worse, here's the scale of the new drug challenge. Ignore a lot of the data and the flow through. But to develop a new drug generally will take at least 14 years from discovery through to it being available to patients. And because of the attrition rate, science is hard, things don't work, drug development is really tricky. You need at least 64 new projects coming out of universities or research departments in order to get all the way through to the end to have one available. To develop one drug all the way through costs typically a minimum of $130 million. But when you take into account the cost of the attrition across the whole range, it's just under $700 million. So quite often you hear on the news that a new drug has taken $1 billion to develop. And that's why, because to get that one drug, people have had to work on hundreds probably in order to get the one that gets there. So $600 million to do it, and we need many more than one new drug. So this is a multi-billion-dollar challenge. Thankfully, the world is responding. There was a United Nations General Assembly 3 years ago that committed all countries to invest more in AMR. The AMR Centre is part of that initiative. We help SMEs and research institutes from around the world to accelerate their really good new technology from preclinical development and get them into patients as quickly as possible in clinical trials. There are no major pharma companies in the UK working on antibiotics. So we've had to rebuild some of that capacity over the past few years. The other thing that's happened also is that the World Health Organization has helped to focus attention by identifying the key pathogens and the key diseases where we have no current treatments in the pipeline and we have to refill that. So it is a positive story, but there's a hell of a lot of work to do between now and having a new armory of antibiotics to fight these superbugs. And don't forget, in the 14 years it takes to start the research now to develop a new drug, that's a long time in the microbe world. So new resistance mechanisms will develop. This will be a never-ending battle. It's us against evolution. Someone said the bugs have had 4 billion years to get ready. We've only had probably less than 1 million years to prepare this. So, main message from me today is whether you're a scientist in the lab, whether you're a chemist, a biologist, whether you're in public health, whether you're in veterinary science, we need more people to join this battle, this mission to tackle AMR. Jim O'Neill's review came up with these 10 commandments. So the things that we need, more public awareness. So being here today is part of that. Public health measures, a lot of that is being put into place in the UK already. You try going to a GP and getting an antibiotic prescription. It's now a lot harder than it used to be for a good reason. The overuse of unnecessary antibiotics has in part led to this problem. Agriculture, there are more antibiotics used in animals than there are in people. So, in China, horrifically, and in India, colistin, which is our last line of defense drug for many of these multi-drug resistant organisms, is used in chicken feed as a growth promoter. It's banned here, banned in the US, but it's still going on. And then the epidemiology, so scientists understanding the genetic makeup, whole genome sequencing of these organisms to be able to trace them back to the site of origin and understand how resistance develops. But for us as scientists, lab workers, chemists, whatever, we really need new treatments and diagnostics. So the work that's going on here is hugely important in helping develop those new technologies and apply them to the AMR agenda. International coordination and collaboration is also essential. Many of the programs we support are also supported by other international bodies, and clearly there are some threats on the horizon from Brexit, but we're hoping that can be overcome by sensible working approaches between UK and the EU. But most importantly, it's the reinvestment in programs. So to find this $600 million to develop new antibiotics, and for more people like yourselves to become enthused by the challenge of this and to get involved in projects that are going to develop that next generation of technologies and therapeutics. But finally, if you're not convinced by me, what I'd like you to do is just listen to this next video, which is about 3 minutes, and then that'll be the end. This is what the patients that are being affected by this are saying. So let me just do that for you.
My first encounter with antimicrobial resistance was in 2004 when my mum was being treated for cancer. The surgery went extremely well. Within 2 days she started with rigors and being very sick and was very ill and was told she had an infection. She was actually being treated with the drug vancomycin, so I came home and I did a bit of research, and that's when I found out it was the drug of last resort for MRSA. My mum's condition got worse. She was in hospital with the infection for about 6 weeks and she ended up passing away at home. But we researched her medical records after she'd passed away, and we did actually find that the wound that was infected was actually still colonised with MRSA when she left the hospital. It wasn't my first encounter with infection, however. 34 years ago, I lost my daughter to Pseudomonas meningitis. She was only 2 weeks old, and we'd just left hospital. Even though she got to hospital quickly to treat it, she didn't respond to the antibiotics, and she didn't make it, unfortunately.
I've lost 3 family members to bacteria that have been resistant to antibiotics. My stepfather, my grandfather, and my uncle. What happened to my stepfather was that he had a massive heart attack and he was rushed into our local hospital, and he was treated quite well at first. And they moved him onto a general ward after about 14 days, and he picked up an infection. The bacteria did not respond to any form of treatment. Everything they threw at it, it just beat the antibiotic, until eventually he died 15 weeks later from what they called organ failure. All because we'd lost the battle against the bacteria. We could not treat it. Nothing matters until it becomes personal. Now, before my stepfather died, antimicrobial resistance and MRSA were somebody else's problem. Losing a loved one made it my problem, and it helped me form the charity MRSA Action UK. We're never going to stop all infections. That's impossible because bacteria are all over, but we can make the majority of avoidable infections avoidable. And until we do that, I will not rest. This is an issue far greater than climate change. Antimicrobial resistance will affect every person on the planet. Modern healthcare systems now are underpinned by the use of antibiotics. And what I'm trying to say is that without antibiotics, modern healthcare as we know it today would not be able to function.
I hope that the warnings are going to be heeded about antimicrobial resistance, and everybody does understand that they've got a role to play in preserving antibiotics. As far as my granddaughter and my grandson are concerned, I want them to live in a world where antibiotics will work and simple illnesses can be treated, and if they need more complex surgery, they've got the best chance of surviving that.
Okay, very moving testament there from the patients. Please go away from this. If you have the opportunity to get involved in a project that's related to AMR, please grasp it because that will make my visit here today well worthwhile. So thanks very much. If you have any questions, I'd be pleased to answer them. But feel free to go as well if you need to.
Why do you think Big Pharma have been so reticent to take it on? Because it feels like there would be a big market for
Okay. If you go back 30 years, we had the armory that I showed earlier with all the new classes, the recent classes, the innovations that have been developed across the 70s and 80s. There's a widespread feeling that we'd solved the problem. So people switched their attention to new priorities like HIV, for example. So an awful lot of people working on antibiotics got switched into antivirals and the viral threats that came along. At the same time, a lot of the older products were becoming generic. So patients and healthcare providers are used to paying $1 for a strip of generic antibiotics. So you have this reducing price and reduced innovation at the same time. So actually quite a lot of the big pharma companies pulled out of antibiotics research 10, 20 years ago. More worryingly, three big pharma companies have pulled out over the past 2 years. And really that's all down to economics. The prices that are currently paid worldwide for antibiotics aren't high enough to justify the $600 million that I mentioned of investment. It's unlikely, given the current reimbursement strategies, that those drugs will make a profit for their shareholders, and they're very rational, profit-driven organisations. And finally, here's the conundrum that governments are currently trying to tackle. We need really good new antibiotics to address the superbugs that are developing. But we never want to use them unless it's exactly for the patient that needs it. We want to use the old ones in patients that's still susceptible. So it's the ones that really need it that you only want to give it to. You want to hold it in reserve. So there's the conundrum. 600 million to develop it, but really you want it on the shelf as an insurance policy. So I think in future, governments and insurance companies in the US, for example, they're going to have to pay some sort of insurance premium or some mechanism that guarantees that these drugs are going to be on the shelf and ready for when they're needed. Because the current reimbursement price for volume just doesn't work in antibiotics. Okay.